It's my great pleasure to introduce Professor Yabuki from the Kyushu Institute of Technology. I had the pleasure to meet for the first time Tomohide right before the pandemic. We were in Hawaii in 2019, so that's a great way to start a friendship. And it's great to see him now virtually and introduce him here at the Thermal Transport Cafe. This is also a special occasion because this is the 20th talk that we feature by a junior faculty in the thermal transport area. So it's a great honor to introduce Tomohide. He will talk to us about his pool bonding study on water and surfactant using infrared thermometry. With no further ado, Tomohide, please take the floor and surprise us with your work.
Okay. So yeah, thank you, 𝗵𝗲, for inviting me. So my name is Tomohide Yabuki at Kyushu Institute of Technology, Japan. And today I'd like to talk about the heat transfer mechanisms in pool saturated boiling of water and surfactant solution observed by high-speed infrared thermometry. And first, I'd like to talk about the motivation of boiling research. And boiling heat transfer has a large heat transfer coefficient compared to air forced convection and liquid forced convection. That's why boiling has many cooling applications. For example, the cooling of power device and CPU and GPU for self-driving technique, and also satellite electronics. But it's not yet clear why boiling has such a high heat transfer coefficient, and there are still open questions in boiling heat transfer mechanisms. And the better understanding of boiling mechanisms is very important because it leads to development of more reliable numerical simulation techniques and also development of higher performance boiling heat transfer surfaces. In a general boiling experiment, we obtain the boiling curve to evaluate the macroscopic boiling heat transfer performance. But it's difficult to discuss the boiling heat transfer mechanisms based on spatially and temporally average heat transfer data. And on the other hand, the high resolution measurement techniques like MEMS sensor and high-speed infrared camera enable us to directly observe the heat transfer mechanism on the wall. And in particular, the high-speed infrared camera has the advantage of being able to measure this distribution of temperature or heat transfer. And so this is considered to be the most powerful tool to explore boiling mechanisms. And so I employed this technique for the experiment. And as you know, the 𝗵𝗲 is actually a leading researcher of this field. And first, let me explain about the fundamental heat transfer phenomena included in pool boiling. And first, there is the thin liquid film called Microlayer. Its thickness is on the order of 1 micron, and so its thermal resistance is very small, and so it can quickly evaporate under the bubble. And this bubble is grown by the evaporation of microlayer and also the evaporation of superheated liquid layer around bubble. And under in the center part, the dry patch is formed due to the complete evaporation of microlayer, and also the bubble motion induces convective heat transfer, forced convection on the surface. And main targets are to investigate the microscale heat transfer characteristics of these fundamental processes, and also to investigate the contribution of each fundamental heat transfer process to overall wall heat transfer through heat flux partitioning analysis. And today I have two condensed topics. The first one is the heat transfer mechanism in pool saturated boiling of pure water on smooth bare sapphire surface, and then on the sapphire surface with artificial nucleation sites. And second topic is on the mechanisms of heat transfer enhancement in pool saturated boiling by addition of our surfactant. This is the experimental setup. We used high-speed infrared camera to visualize surface temperature of the sapphire substrate from the backside of the substrate, and simultaneously we visualize the bubble behavior from the side. The spatial resolution was 80 microns per pixel, and the framing rate was 3,000 frames per second. And we performed a water pool saturated boiling experiment using this setup. And this is used a schematic of used heated sapphire heated wall. And this is the sapphire substrate with a size of 20 millimeters by 30 millimeters. And its thickness is 0.6 millimeter. And onto the sapphire substrate surface, we spattered titanium thin film heaters with a size of 20 millimeters by 10 millimeters. And we employed to employ the heat transfer analysis proposed by 𝗵𝗲𝗁𝗀𝗿 to calculate the temperature distribution inside the sapphire substrate. I skipped detail, but through the coupled analysis of three-dimensional transient heat conduction inside the wall and also radiative transfer, we obtained the surface temperature distribution and surface heat flux distribution, and also the transfer coefficient distribution. This is the result for the isolated bubble boiling. So here, so this like low temperature region and high heat flux region under this bubble corresponds to the microlayer region. And inside that, we have a dry patch showing very low heat flux. And this expands due to the evaporation of microlayer. And around the bubble, we have the convection region, and then this bubble detached from the wall. And first, I evaluated the contribution of microlayer evaporation to bubble growth. And we calculated the latent heat inside the bubble at the bubble temperature through the by extracting the bubble volume from this image. And this QB is the latent heat, and this QML is the amount of heat transferred by microlayer evaporation. We measured this one using high-speed infrared thermometry. This contribution of microlayer evaporation to bubble growth is around 50%. And this is very similar to the result obtained by the MEMS measurement. And this and the rest of 50% is supplied from the superheated liquid layer. And so I can say if we consider we need to consider both the microlayer evaporation and also evaporation of superheated liquid layer to model the bubble growth for in pure boiling pure water pool boiling. And then this shows temperature distributions, and this is heat flux distributions at each heat flux. And this red one shows the average heat transfer coefficient. And this HTC, average HTC is increased with increasing wall superheat and heat flux, as in the case of general boiling case. This shows heat transfer coefficient distributions for isolated bubble region and coalesced bubble region. And this red high heat transfer coefficient region correspond to the microlayer region, and this low HTC region correspond to the dry patch. And between bubbles, we have convection region. And for isolated bubble region, the convection area shows the very low heat transfer coefficient. On the other hand, for coalesced bubble region, I think you can see very, very small like vortices, and convection region shows the much higher heat transfer coefficient compared to isolated bubble region. So this means the bubble-bubble interaction strongly enhances the convective heat transfer. And this shows the through the image analysis of heat flux distribution, we calculated contribution of microlayer evaporation and convection heat transfer to overall wall heat transfer. And this is the area coverage ratio of the microlayer evaporation region and the convection region. And microlayer region shows highest heat transfer coefficient and also highest heat flux. However, it's because of its small area coverage ratio, its contribution is small, which is less than 30%. On the other hand, like the convection region having largest area coverage ratio shows the largest contribution to overall wall heat transfer. And so far, like I have shown the results for bare surface, but my bare surface was too smooth and had a low nucleation site density. And so the obtained HTC was significantly lower than that of the boarding on a copper wall. So we wanted to enhance nucleation to realize the higher heat transfer coefficient comparable to the copper wall. And on the other hand, the Mateus group have developed very nice special heaters for infrared experiment. In this case, yeah, to get more general findings. And in this case, they prepared copper-plated layer, so we can scratch the surface to simulate the rough metallic surface. And also in this case, they used the laser machining to prepare artificial nucleation sites on the metallic foil. And in our case, we employed inkjet printing of superhydrophobic agent glycol to form artificial nucleation sites. And this shows the photograph for the single superhydrophobic spot with a diameter of 150 microns. And I tried to make it smaller, but we failed at. And so this is the slightly larger than the size of the general cavity size on the metallic surface. But anyway, we employed the staggered arrangement of the nucleation sites, and we tested 5 kinds of five densities, and this shows the corresponding spacing between nucleation sites. And this shows the temperature and heat transfer coefficient distribution at 0.3 megawatt per square meter. And in this selection, the nucleation site density is increased. And we can see the bubbles are well aligned on the surface. And so we confirmed that the prepared superhydrophobic spots will act as a nucleation site. Then this is the obtained heat transfer coefficient, and we succeeded to enhance the body heat transfer coefficient, and basically the heat transfer coefficient is increased with increasing nucleation site density. And here, this shows the result of heat flux partitioning analysis, and this shows the contribution of microlayer evaporation. And this shows a contribution of the convection to the total wall heat transfer. And this shows the area coverage ratio of the microlayer. And this is that for the liquid phase. And these two figures are a little complicated, but the important message here is even with the enhanced nucleation, the area coverage of microlayer is still small compared to the convection region, and so this contribution is small and is less than 35%. And on the other hand, like liquid phase convective heat transfer shows the largest contribution. So the convection dominated wall heat transfer. So next, we want to know how the convection effectively transfer the heat from the wall. And it's almost impossible to experimentally measure heat and fluid flow just on the surface. And so now we are doing the numerical simulation through the collaboration with the Dr. 𝘀𝘁𝗂𝗿𝗁 at Post-rewetting Institute to elucidate the convective heat transfer mechanisms. It's just ongoing research. So then I'd like to show the observation result of the Microlayer under large mushroom bubble. And so here, so here is the wetting, and this liquid layer region shows the uniformly the low heat transfer coefficient compared to the general convection region. And this liquid layer region is considered to be a Microlayer created through the bubble coalescence. And this liquid layer is confined to a very small space between interfaces. And so liquid inside cannot freely move. And so the convection is suppressed. And that's why this Microlayer region shows lower heat transfer coefficient compared to the general convection region. And I played video. For example, yes. For example, here we have Microlayer, and then yes. So yeah, here we have Microlayer region, and finally, I think we have very large Microlayer here. Yes, here there's a very large Microlayer under this mushroom bubble. And however, we couldn't observe the Microlayer on the bare surface, having less nucleation site density. So this means a certain number of nucleation sites is necessary for Microlayer formation. And this is the result for larger nucleation site density. And we have here Microlayer under this large porous bubble. And then this Microlayer disappears here as this mushroom bubble detached from the wall. And at this time, we can see another Microlayer here beneath this large porous bubble. And we observe the Microlayer in the wide nucleation site density conditions. And here I estimated the Microlayer thickness from the average heat transfer coefficient in Microlayer region. And that was 30 to 40 microns. And the Professor Sakashita in Hokkaido University measured the Microlayer thickness using this conductance probe. They show somehow a little larger value. And now I don't understand the reason for the difference. However, I think the Microlayer thickness determination mechanisms and Microlayer formation condition will be very important research topic. And then this shows the formation process of large dry patch. here, and this is the magnified view, and before the formation of dry patch, there is a macro layer, and then the large dry surface appears on the surface. And these snapshots show that the before the formation of large dry patch, there exists a macro layer here and here, and depletion of this macro layer due to evaporation and also the wetting motion results in the formation of large dry patch under mushroom bubble. And after this like large dry patch was rewetted by the liquid, rewetted after the departure of the large mushroom bubble. And so we don't have now the data for information about boiling crisis. And so now we are doing an experiment to investigate the relation between macro layer behavior and critical heat flux. And also we use the very well designed, well aligned nucleation sites. And so it's necessary to confirm whether the macro layer is formed even when introducing the randomness of the arrangement of nucleation sites. Yes, and from here I'd like to move on to the next topic on heat transfer enhancement mechanism by surfactant addition, and this shows the effect of surfactant addition on the interface properties. And absorption at the solid-liquid interface changes the wettability of the surface, and also absorption at the liquid-vapor interface generally reduces the surface tension. And this addition of the surfactants dramatically change the boiling behavior. And so this is water case, and these two are for surfactant solutions. It has long been well known that the surfactant addition can easily enhance the boiling heat transfer. However, to my knowledge, there's no direct observation of the wall heat transfer, or surface heat transfer behavior in the surfactant boiling. And so the mechanisms of the heat transfer enhancement has not been clarified yet. And so we performed the infrared 𝗀𝗄𝗃 experiment for the surfactant solution. And the experiment setup is the same as the pure water case. And in this case, I used the spacing of 1 millimeter. And important thing is the used surfactant. And we selected the non-ionic surfactant, polyglycerol for 𝗀𝗃 ether. And I set the concentration at 0.2 gram per liter because we confirmed that the boiling is significantly enhanced at this concentration in the preliminary experiment. And the surface tension was reduced to almost half of the pure water value. And these two show the criteria for surfactant selection. And the first one is the non-ionic surfactants because of its low corrosivity to metal surfaces. And another is the ether type surfactant because of no hydrolysis of surfactant molecules inside the water. And this shows the result for the pure water and surfactant solutions. And this shows the heat transfer coefficient for surfactant solution and pure water. And we confirmed that our addition of our surfactant greatly enhanced the boiling heat transfer. And also there is very big difference in boiling bubble behavior and wall heat transfer behavior. between pure water and surfactant. And first, the addition of surfactant can suppress the bubble coalescence. And so for surfactant solution, there are so many isolated bubble rising in the liquid. And also the surfactant solution case shows the much larger microlayer area compared to pure water case. And so the important thing is the surfactant addition greatly enhance the area coverage of the microlayer. And then I'd like to discuss about the heat transfer enhancement mechanisms. And here, boiling heat transfer coefficient can be approximately expressed by this equation. This shows the area coverage ratio of microlayer for pure water case and surfactant. And this is so A over A. And so for pure water is small, as I said. But the important thing is the surfactant addition greatly increased the area coverage of microlayer. And also this one shows the average heat transfer coefficient in microlayer region, HML, or this one. And somehow the surfactant solution and pure water show similar value. That's why this is almost constant, this increase of area coverage ratio by addition of the surfactant was found to be a mechanism of the boiling heat transfer enhancement. And also this is the interesting result. So this is contribution of microlayer evaporation to overall wall heat transfer. For pure water, it's small. That's smaller than below 30%. But for surfactant, it exceeds 50%, and microlayer evaporation dominated the wall heat transfer in the surfactant boiling. And then I'd like to discuss about 3 factors increased microlayer area with surfactant addition. And the first thing is the softening of bubble due to the reduction in surfactant surface tension. And the second one is separation of bubble coalescence. The third one is sliding motion of primary bubbles and formation of microlayer under sliding bubbles. And these first 2 result in the very tight packing of the bubble on the wall. And for pure water case, the primary bubbles merge with the large coalesced bubble, mushroom bubble at the top. And so this results in the smaller area coverage of bubble on the surface. On the other hand, for the surfactant addition suppresses the bubble coalescence, and also bubbles can be deformed easily into the complicated shape because of bubble softening. And these 2 effects result in the larger area coverage of bubble on the surface. But if the bubble bottom are dried out, boiling heat transfer coefficient will be rather low compared to pure water. And so microlayer must exist under bubbles to achieve the higher heat transfer coefficient compared to pure water case. So we need another mechanism. So here in this video, so first you can see so many primary bubbles tightly packed on the surface. And also you can see these bubbles are sliding on the wall, moving on the wall. And also there is a microlayer under sliding bubbles. And so we found that the sliding motion of primary bubbles and also the formation of the microlayer under sliding bubble is another factor of enhancing the area coverage ratio of microlayer. And also, so there's almost no dry patch because the microlayer quickly move on the surface. And here, this is the sliding velocity extracted from the HDC distribution. And here we calculated microlayer evaporation time, which is time required for all of microlayer evaporates. And here the microlayer thickness was roughly estimated from the average heat transfer coefficient of in the microlayer region. And we use the average microlayer average heat flux in the microlayer region as a evaporative heat flux. And then we calculated bubble travel time, which is time required for bubble to travel a distance corresponding to the 1 microlayer size, which is 2 millimeters. And we use this sliding velocity here. And this shows the red one is the bubble travel time and the blue one is evaporation time. So travel time is significantly smaller than evaporation time. So this means the sliding bubble has the enough large velocity to prevent the formation of the dry patch. So the bubble quickly move on the surface, and so the dry patch cannot form under the bubble. So and then this for surfactant solution, the boiling curve can be classified into 3 regimes, and for isolated bubble regime, there's almost no bubble coalescence. And even in the surfactant solution, in high heat flux condition, there is the bubble coalescence, and this bubble coalescence forms large mushroom bubble and macrolayer and large dry patch under the mushroom bubble. And finally, I'd like to show the observational result for the macrolayer formation process and in the dry patch formation process. So this shows the macrolayer formation process, and this superheated liquid between bubble is evaporated, and this evaporation results in the coalescence of the bubble in a high heat flux region. And in this bubble coalescence process, this liquid between bubble move onto the wall surface beneath a coalesced bubble, and this forms the thicker liquid layer, macrolayer. And repeated coalescence of bubbles form a larger macrolayer. And in this case, after the coalescence of 2 bubbles, we can see a lot thicker liquid film here. And in this case, first you can see many primary bubbles, and after the coalescence here from here, and then after the coalescence, we can see large dry patch after the coalescence of bubbles. And then this shows the result. This is the result at the maximum heat flux in our case. And there you can see the very large dry patch under the large mushroom bubble. However, the dry patch is rewetted after the bubble detachment. And before the formation of large dry patch, we can see very large macrolayer. And in this high heat flux condition, there are so many bubble nucleation even under the macrolayer, and so you can see many microlayers, lead ones, in the macrolayer region. And after this one, due to the depression of the macrolayer, this depression of macrolayer results in the formation of the large dry surface under large mushroom bubble. And so we couldn't observe boiling crisis process. However, we found that the Microlayer depression leads to the formation of large dry parts, as in the case of the pure water. And let me summarize my talk. For pure water, convective heat transfer dominated wall heat transfer, and contribution of microlayer evaporation to overall wall heat transfer was small, which is less than 35%. And microlayer was observed on the heat transfer surface with artificial nucleation sites. And for surfactant solution, I tested just one type of surfactant and one type of concentration. Microlayer evaporation dominated wall heat transfer, and increasing in area coverage of microlayer was the mechanism of heat transfer enhancement, and double softening and double coalescence separation and microlayer formation under sliding bubble resulted in the increase in microlayer area. And depletion of microlayer beneath mushroom bubble led to formation of a large dry surface. And let me thank my students and collaborators. And so, yeah, that's all of my presentation. Thank you for thank you for your attention.
On my end, I want to thank you again and thank you all for attending this talk. This was a very lively session, and I truly appreciate your presence. Thermal Transport Cafe will take a short break, and so with Tomohide we finish the spring session. We'll meet you all again in the fall with more talks. And well, thank you very much again, and I hope to see you around the world for different conferences that we have in the weeks to come. Thank you all, and stay well, and see you soon.